Okay, so hi guys, so let's find the transfer function of this particular system. So the rod is supported by bearing at either end, at this point and at this point. So we're writing the first equation. When the torque is applied in this direction, because this means angular displacement. So torque is applied in that direction. This damper will resist the torque, as opposed the torque rather. So it's going to go in this direction. This inertia actually is not mass per se, it's inertia, but it's the equivalent of mass for rotational motion. It's going to also oppose the torque's motion, and this spring is going to oppose the torque's motion. But notice how the spring is in between J1 and J2, which are rotating at their own angular displacement. You see how that will come to play in the formula. So for the formula, we're going to have sum of applied forces is equal to sum of opposing forces. In this case, the applied force is T of T, that's the torque, which is equals to the opposing forces. The first opposing force here is the damper, so it should be D1 times the angular velocity, which is d theta 1 T over dt. The second this thing that's opposing the torque motion is this inertia. So it's going to be mass, sorry, inertia, not mass, but they are is the equivalent. J1 mass times acceleration. So J times acceleration, angular acceleration in this case to be d square theta t over dt plus now this k. Notice how remember I said that it's in between the two masses. That means it's affected by both of their rotations. So it's going to be theta 1 minus theta 2. Basically the angular displacement of the inertias. Now we can just take the Laplace transforms of each of this. It's going to be t of s equals to Laplace transform of this will become d1 s theta 1 s plus j1 s squared theta 1 s plus k theta 1 s minus k theta 2 s. You can use this table as a guide. You can see k, c means k, d becomes ds, and j becomes j squared. And then simply write your theta in the s domain. So now let's focus on j2. In this case, there's no torque that will be applied. So the only motion is done by the spring and is resisted by the inertia and the damper. So it's going to be 0 equals to, since there's no applied force, equals to J2. Rather than writing, I'm just going to write theta dot dot 2 plus D damper 2. I'm just going to write theta dot, that's velocity, plus K, in this case it will be theta 2 minus theta 1, since you're working in reference to theta 2 movement. So it's going to be theta 2 minus theta 1, but here it's theta 1 minus theta 2. You get the point. Equals to 0. Now we can simply take this to the Laplace domain, which in this case it will become this. Now I always like to factorize. So take everything that's theta 1 to one side and what has theta 2 to another side. I've also done the same for this. So this is equation 1 and this is equation 2. Now what we're looking for is theta 2 over ts, right? So let's look at which of these equations has ts and theta 2. You can see that this equation has ts and theta 2. So if you can find the way to substitute out this theta 1s, you should go for that. So we can make theta 1s of your formula here. Before that, I would like to assign some certain things to make our lives easier. So you can just make this to be b, make this to be a, make k to be b, make k here as well to be b, and sorry, make here c instead. So in this case, it's going to be 0 equals to b minus b theta 1 s plus c theta 2 s. Theta 1 subject formula, theta 1 is going to be equals to c over b theta 2 s. Now let's substitute into this equation. This equation became Ts equals to A theta 1s minus B theta 2s. Put this into it, it's going to become equals to AC over B theta 2s minus B theta 2s. Since theta 2s is repeating, might as well just take it out. Here, make here LCM. It's going to be AC minus B square. And you can simply make theta 2s over Ts and it equals to B over AC minus B square. Now simply just substitute back what A, B, C was. So this is just a simple way of getting answer. J1s square plus D1s plus K and J2s square plus D2s plus K minus K square.